Hi, Tara. Deborah.
Hello.
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 Hi, Deborah. And Dion's coming. I don't know about Alexis. She's been staring at computer screens too long. She's got a bad crick in her neck, I guess. I don't know.
Yeah.
Okay. You tell her to take an Advil. Come to class. You heard that when you watch this, Alexis. If you don't show up, okay. All right. So so guys, let's what I wanted to do was to look with you at some more of that homework. I've got a key for the homework that I gave you on the power series representations of functions, and then I want to finish that section. I'm probably about a day behind, but that's okay. We'll figure that out. Let me share the screen with you and see where we are. It's almost Friday again. We're just clicking the weeks off. Okay. All right. So, so guys, yesterday we talked about these representing power series as functions, and I gave you some homework. Actually, I made a key, and I think I wrote something down wrong on the key, but I've got the key. But let's review what we were doing first of all, and then we'll look at the key, and I'll ask you if you've had any chance to do this. But if you haven't, then we'll kind of go over it, and you can do it tonight. We're not going to do a whole lot new today. Just finish up this section on power series representations. All of this depended on putting this whatever function you're trying to represent right now in the form A. Oh, sorry, wrong. And I want my red pen. Hang on. Putting it in the form of a geometric series. Okay, so you want the sum to be 1 over, or A over 1 minus R. So if you can get it in that form, you can identify the A, and you can identify the R, and you'll have the sum from n equals 0 to infinity of A R to the n. And you will have represented that in the interval that it converges as that function. So honestly, guys, tell me who's looked at this homework yet. Okay, Tara, you looked at it. Dion, you looked at it yet? No, you did. Deborah, did you look at it? Okay. All right. I've got a key, but I'll tell you what I'm going to do. I'm going to just work another problem like this. I'm going to take one out of the book because there were some in the book. I didn't assign the ones in the book. I assigned these. And let me say that I think on the key, I did this one for 2 instead of -2. I was doing it in a hurry, and I thought, yeah, I did it for -2. But I'll show you the key and the parts of it I have, and then you can redo it. So this is still in section 11.6, and let's see. And the homework on that particular page, I'm going to give you some more homework on that page tonight that has to do with the rest of the section. But the homework on that page, it's on page 579, looked like initially, I'll go to the bottom here and add a page. So, oh, there we go. The rest of that's my lecture for the day. But the problems there on page 579 look like the first part of it said find a power series representation, define the power series, and so on. And they wanted you to do in a certain interval, but one of these might look like this. F of x is 1 over 1 minus 3x. Actually, that one's really easy because it is in this form already. There's A, there's the 1 that you need, and the R, it looks like, is 3x. Okay, the R is 3x. So what you know then is that this thing converges where the absolute value of R, or in this case 3x, is less than 1. And what that means is that 3 absolute value of x, you can bring that out, is in between 1 and -1. Not absolute. It comes out of the absolute value, guys. I don't know why I keep doing that. It comes out of the absolute value once you put it in that interval. It looks like that. And then if you divide by 3, you get 1/3 and minus 1/3. So the first thing you find out is there's the interval that it converges in, okay? Now what we want to do is write it. It's pretty easy to write. It's going to be the sum from n equals 0 to infinity. My a was 1 in this case, so 1. My r was 3x, so I'll write that to the nth. And these were all about 0, okay? These were all around 0. They didn't tell you that in the book, but that's what it is. I will say a couple of things about how we write these things. Sometimes you'll see the answer in the back of the book where this is actually carried out. And it might look like 3 to the nth, x to the nth. I know that in some of the ones that were in the homework, you didn't have a key for it, but you can write the answer a lot of different ways. So I'm really trying to make it look like a geometric series. I'll give you another one here. Suppose we had this one, and this one looks different. Suppose it has x squared over 1 minus x squared. No, I don't want to do that one. Suppose we had 2. Suppose we had 3 over 2 minus x squared. Let's do that one. All right, and I want to represent that function as a power series. I need to make it look like geometric series again, so I really need a 1 where that 2 is right there. So I'm going to divide everything by 2 first. So that'll be 3/2 here. 2 over 2 is 1, and then minus x squared over 2. So now it looks like I want it to look. A is 3/2. R is x squared over 2. And this is going to give me an opportunity to show you what I mean about rewriting things. This is going to converge where the absolute value of R, or in this case, x squared over 2, is less than 1. That says x squared is in between 1 and minus 1, which also means if, and this is a little different, guys, but if x squared is in between minus 1, then x has to be in between minus 1. If you don't believe that, pick something outside the interval, like 2 or 1.5, you'll get an x squared that's bigger than 1. Okay, so that's what that looks like. Tiara.
What happened to the 2?
Oh, it's a 2 here. Oh, sorry. Thank you. It disappeared on me through my carelessness. How about that? Looks better. Thank you. Okay. So I multiplied through by 2. Now, if I want to write the series, it'll look like this. N equals 0 to infinity. And we'll have A, which we've decided is 3/2. So I'm going to put that 3/2 in there. I can pull the 3/2 out, but I'm going to show you something about how the book will sometimes rewrite this. We know that the R is x squared over 2. So A is 3/2. R is x squared over 2. So that's my AR to the nth right there. Now, let's talk about how the book might give you the answer here, because it might not look like that when you see it. Is everybody okay with what I did there, though? Here, you worked on it. Dion, you might have worked on it. Is this looking okay? Okay. So, all right. So what you might see is something a little different. They might try to combine some things. So, for example, if I had 3/2 here, and I raised both of these things right here to the nth power, I'd get x to the 2n over 2 to the nth. And that gives me, or whoever's rewriting it, sort of an opportunity to combine something down here. What's 2 times 2 to the nth? If I were to rewrite that, what would it be?
2 to the n plus 1.
Exactly. It would be 2 to the n plus 1. So what you might see in some of these solutions, I tried to show you how I was writing it differently, but you might see something like that. But if you write the terms of that out, I mean, suppose you let it be something between 2 and minus 2, you would see a geometric series. Okay. Now, interesting about this geometric series, the powers of x on it are all going to be what kinds of numbers? If it's 2n, what kind of number are all the powers going to be?
Even.
Even, exactly. They're going to be even. If this had ended up being 2n minus 1, all the powers would have been odd. Now, that's going to show up in a really interesting way tomorrow and possibly on into Monday. Okay? But that's what that one looks like. right, let me show you what I'm going to put online. Let me show you the key for a second here, and then we'll come back to this. Where'd it go? Here, it looks like this. It says on it, it's key for power series representations. I just took the ones that I gave you on the homework, and some reason it didn't scan in very well. But I looked at what we were looking for, a geometric sum. I identified, I did whatever I had to do to the function to identify A and R. And then I wrote the series. You can see right here where one of those, I rewrote like I suggested a minute ago. Since A was a half and I had a power on 2 down here, I wrote it as 2 to the n plus 1. So I'll let you look at that. Another one I wanted to look at was, which one was it? Let's see, 2, that one. 4 was about, I messed up on, I think I wrote 4 as C equal 2. No, about C equal 2, where was it? Not there. Where'd it go? Oh, right here, number 3. If I want to have it in powers of 2, I'm going to have to subtract 2. Now, pay careful attention to this because it's a little bit tricky to get it rewritten right. You want the x minus 2 to be in parentheses, and you've already got a minus x there. So you want a minus 2 there, but if you look at the minus in front of it, that means you're actually adding 2 under here, which is why I subtracted 2 right there. I had to have that x minus 2 in parentheses for it to be my r. So you can always check to see if you're right, because when you add everything up and you distribute it out, you should get what you started with. For instance, in this case, I'll have 3 minus x minus a minus is 5. When you add it to the 3, and I got 5 minus x. Just have to manipulate it so you've got that in there, because that's what you want to have it centered at 2. I actually think you've got this one. I actually put on the homework, I wanted to have it centered at minus 2. Then what would I need here if I wanted to have it centered at minus 2, guys?
X plus 2.
I'd have to have an x plus 2. So if I put a plus 2 in here, I would have been subtracting 2, which means I would have added it over here. So just take another look at that one. There's one other one I want you to sort of think about when you do it. This one, right, one of these I ask you to do partial fractions on. Now, number one, I'd like for you to check my partial fractions because I did it in a real hurry right before I had a Zoom meeting at noon. But I split it up, and I think it's split up into 1 and 2. So both of these I may want centered at 0. If I center this one at 0, it's going to have a radius of convergence between minus 1 and 1. If I center this one at 0, because there was a 2 here and I had to divide, it's going to be between 2 and minus 2. You got to pick the common interval where both of them will converge, because this is a single function. So the smallest interval right here that would be inside this one would be from minus 1 to 1. So if I wanted to say, well, what's my interval of convergence for this thing right here? You would pick this one because it's included in that one. It's the smaller one. You don't want anything bigger than 1 here, because it was okay here. It was okay in this one, but it would not be okay in that one. So when you put the 2 together, you've got to have the smaller one. Okay. I think I mentioned that yesterday. Okay. So work on that, and I will post. I know I already have posted this on Moodle. You've also got it kind of to glance at on here if you watch the video. But I posted on Moodle. Do that homework, and we'll talk about that. If you have any questions with it. I will probably tomorrow give you a few of those problems to do that'll be due on Monday. So be sure you look at it tonight and make sure you understand how to do that. Okay, there's a little more that I need to talk about on power series representations of functions. Let me go back to where I stopped here. In those problems I just showed you, we were really relying on the fact that we could write something in the form of a geometric series. Well, not all functions can be written in the form of geometric series. It's those nice ones that were sort of rational functions that had a certain look about them. But for example, if I said to you, I'd like for you to find a power series representation for sine of x. Well, there's no imaginable way to write that as a over 1 minus r. So I got to have something else here. Another one might be cosine x, or another one might be e to the x. Those are all functions that actually do have power series representations, but I can't put them in the form of a geometric series, which I know the sum of. So what I'm going to do is introduce something to you that allows me to do some of that. And then tomorrow I get the big guns, which are called Maclaurin series and Taylor series, which says, give me any function, I'll be able to do that. Now, ultimately what you need to do, it says, suppose a power series has a radius of convergence bigger than 0, and let f be defined by that series right there. Ultimately, what we need to do is find out what these coefficients are. We will do that when we talk about Taylor series and power series, because, I mean, Taylor series and something called Maclaurin series, because it'll tell me how to figure out what those coefficients are based on what the function is. Now, we don't have that quite yet, but I'm going to make a statement here that says this: if we can get a series representation, then we can get a series representation of its derivative. And you know why? Because all I have to do to take the derivative is take the derivatives of these things. And that will give me the series representation. So for example, if I start with this, and I want to find f prime, right? I will just differentiate this. So guys, what's the derivative of a sub 0? Well, it's just a constant, guys. It's just going to be 0, right?
0.
What's the derivative of a1x?
A1.
a1. Now, notice that's what I'm doing down here. I'm taking the derivative. I got a1. When I took the derivative of that, I got of the x squared, along with the a2, I got 2a2x. This one right here is 3a3x squared. If I look at the last one, you'll bring down the n here, right there. So it'll be n a(n) x to the n minus 1. Now, let's talk about one other thing that you might not notice. This function right here, the series representation started at 0. Now, I can kind of start it where I want to, but if this one starts at 0, let's look at the derivative. If it started at 0, and I plugged in 0 to all of these things right here, what would I get? I mean, I wouldn't even get anything that I needed. But if I start at 1, then if I put in 1, I'll get a1. That's sort of what to look at there. You want to know what's your first term. If it's a1, then start at 1. And does it work with the x's? Well, yeah, because 1 minus 1 is 0. X to the 0 is 1. I'll just get a1 there. If n is 2, the next term will be a2. X to the 2 minus 1, which is just x to the first, and so on. All right. Now, if I look at the last one, all the way, well, the n minus first, this is actually the nth one right here, because I've got n minus 1 of these and then one more of those. What we're basically saying here is that if you take a derivative, this thing's going to move up 1. If you took a second derivative, where would this thing need to start at? Well, it would need to start at 2. Okay, yeah, it would need to start at 2, because what would happen is the next derivative would be, the second derivative would be, the derivative of that would be 0, then it would be 2a, then you would differentiate this. We call this differentiating term-wise. So this series has a lot of terms. You can find its derivative by differentiating. This is the original function. We can find its derivative by differentiating each of these. Okay. Now, what that does is it makes it easy. If I know a power series representation, I can find the power series representation of f prime easily, even if I couldn't differentiate for some reason. Okay, look at this one. The same thing can happen when you take an integral. So suppose I'm going to take the integral from 0 to x. So I'm going to take the integral and I'm going to plug in 0, it'll wipe out, and then it'll plug the x in, which is what I want. I want it in terms of x. I am going to take the integral of this one up here, and let me see if I can get down back to the original back to the original one. Yeah, right there. There's the original right there, guys. That was the original function right there. So looks like that right there. If I integrate that term-wise, the integral of a naught, and that's just a constant, is the integral of 5 is 5x. The integral of 10 is 10x. The integral of a naught, or a sub 0x, is a naught x. The integral of a1x is a1x squared over 2. The integral of a2 is a2x cubed over 3. The next one will be a4x to the 4th over 4. Because it's just a nice simple power series with powers in it, these are easy to integrate. They're very easy to integrate. Now, I'm sorry Alexis isn't here because this is a great example of when she asked me the question, well, what am I going to do with that? Okay. There turns out to be in statistics a really important curve, and I'm going to kind of write over this, and it looks like that. I don't know if any of you took statistics in high school. You might have, but what does it look like? What does that curve look like to you guys? If you're thinking about statistics.
Normal distribution.
It looks like a normal distribution. It looks like the normal curve, right? Where you've got a certain portion of the population, say 68% of the population is average. And then I don't know what the other percentages are. After that, you've got the whole 68% is 0.68 probability. So the area under this curve should be 1, because you should have grabbed every human being there under that curve. I mean, they're either going to be average, or they're going to be above average, or they're going to be below average at a certain level, okay? So what we say is that the area under this curve is 1. Now, and we know that the area under a curve is the integral from somewhere to somewhere. So in this case, maybe it's minus infinity to infinity to catch all the humans that are under that curve. But I want to tell you that it's got, and I'm not writing the entire thing here, but it's got that term in it. And there's no x in there. There's an e to the minus x squared, but there's no, I mean, if you were going to do this easily, you would need to let that be u, and there'd need to be the du would have an x in it. You need an x in here. There's no x in there. I don't know how many of, I'll try to look up the exact formula, but that's what it looks like. I would need to integrate that. And if suppose I want to know what's the probability that you fall between, you know, here and here, then I would set those limits, and I would have to try to integrate to find that. But I can't integrate it by normal means. What happens is that I'm going to be able to find a series that will express that. And it's easy to integrate a series, because we integrate a series just by looking at this function. Now the question is, how do we get that as a series function? And that's what I'm going to show you today. I'll show you that at the end of class. All right, so let's look at something here. So I can integrate term-wise, and I can differentiate term-wise. And the series obtained, whether through the integral or the derivative, has the same radius of convergence as the original series. So if the original series converge between -1 and 1, so will the integral, and so will the derivative. Okay. Now, what this allows us to do is to find more series representations of other functions that don't look like geometric series. Okay. So here's something nice. Who's out of the picture there? Oh, it's Deborah. Okay. Oh, I'm looking at her seat. There you are. Okay. Okay, guys, we have seen this series before. And it's not geometric. You can't get from here to here and here to here and here to here with any particular R here, because this number, this 1 factorial, 2 factorial, 3 factorial is not cooperating. If you try it, you'll see that it can't be done. For instance, this would be a 1, this 2 factorial is 2, 3 factorial is 6, that's 24. You can't, suppose I wanted to get from here to here, I'd have to multiply by half. But if I multiply by half, I don't get to here, okay? So I don't have a way, it's not geometric. It's not geometric. But so the answer is, what is it a function? Is it the series representation of any function? Well, I want to do something here that I think you find kind of interesting. If I take this as my function and I take the derivative, let's do that. What's the derivative of 1, guys? What's the derivative of 1? It's 0, isn't it? So that first one down here, I didn't even put it there, but the derivative of 1 is 0. Now, tell me what the derivative of x over 1 is. What's the derivative of x over 1? Derivative of x is just 1. So that's what that one is. Okay, so I've got my arrow kind of pointing in a bad direction there. Okay, the derivative of that, let's do this. The derivative of that was 0. The derivative of that is 1 because it's just x. If I looked at this one, 2 factorial is 2. If I took its derivative, it would be 2x, because that's the derivative there, over 2 factorial. 2 over 2 is x. So that's the next derivative there. All right, that's x. If I looked at 3 factorial, I bring down the 3, that would be 3x squared. I'm going to just differentiate that up here, guys. That would be 3x squared over 3 factorial. And I want you to notice what happens here. The 3 in the bottom, 3 factorial is 3 times 2 times 1. All right, 3 in the bottom is 3 times 2 times 1. The 3's go, so that ends up being x squared over 2 factorial. That's that one. We'll do one more. Look at the derivative of x to the 4th. Which one did I just did? I did x2 over factorial. Let's do this one right here. I did x to the 4th. If I differentiated that, that would be 4x cubed over 4 factorial, which is 4, 3, 2, 1. 4's go, and I've got x cubed over 3 factorial. Now, what I want you to notice here, through all my scribble, look at the original series and look at this series right here. What do you notice about the original series and the one I'm getting when I differentiate, guys? So I'm looking at these two right here. You get one, both of them have a 1. Both of them have an x. Both of them have an x squared over 2 factorial. The next one was x cubed over 3 factorial. We just showed, we can show the next one's x to the 4th over 4 factorial. What do you notice about these two things?
They're the same.
They're exactly the same. They're exactly the same. So here's my question to you. What function behaves like this? What function behaves so that it's its own derivative?
E to the x.
E to the x. Guess what, guys? This thing right here, if x is any real number, f of x is this series representation. And that was, you know, that's kind of special. I mean, e to the x is a special function. It's its own derivative, and it works that way for series. So if you got a series that's its own derivative, it's got to be e to the x, okay? So that thing with those factorials in it is e to the x. Now, let me pull out your calculator for a minute. Suppose I said, I want to estimate e to the 0.2 using the first 3 terms of that series. Okay, I want to estimate, and by the way, I'm going to show you in a minute where this thing converges, okay? We're going to use a power series, a ratio test to show you where it converges. But if I said I want to use the first 3 terms to find out an estimate for e to the 0.2, I would put in 0.2 for these terms. So 1 plus 0.2 plus 0.2 squared over 2 factorial. And if you do that, what I got, and you can compute it yourself, guys, you can check me, but I know I'm right because it came out close to what I know it should, you get 1.22. Now, what if you found e to the 0.2 on the calculator? You get 1.221402758. That's what you get on the calculator. This is an estimation of it using 3 terms of the series. So you can estimate that for as far as you want to go. Now, the further you go down the line in the series, the better estimate you get. You know what? I'm gonna try that 0.2 and see if it came out exactly 1.22. I think it did. I don't think I actually rounded anything. So 1 plus 0.2 plus 0.2 squared divided, oh, I messed up something. Hang on. 1 plus 0.2 plus 0.2 squared divided by 2. I can't do anything right. I multiplied by that. Y'all check me. Is it just 1.22? 1 plus 0.2 plus 0.2 squared divided by 2. Yeah, it's just 1.22. But that was a pretty good estimation. It was good at least to the 100th place here. Okay. Let's go further down in the function and see what happens. So let's suppose we did it using the first 4 terms. 1 plus 0.2. Now here are the terms. 1, 2, 3, 4 terms now. 1 plus 0.2 plus 0.2 squared over 2 plus 0.2 cubed over 3 factorial is 6. Okay, everybody, if you got a calculator, do this for me because I've been making mistakes, so you can verify what I say. 2 squared divided by 2 plus, the last one was 0.2 cubed. 0.2 cubed. And then that's going to be, I need parentheses there. What, all right, hang on. 0.2 cubed divided by 6, don't put that in parentheses. 0.2 cubed divided by 6. Okay, tell me what you guys are getting. Anybody? What'd you get when you took it out to 4 places? Anybody?
1.221.
And then was it a bunch of 3s?
Uh-huh.
Okay. So guys, that one, when I went a little further out in the series, it was good to 3 places. The further I go, the closer it's going to get to this. That means it converges. Okay, that converges. That's the series representation for e to the x. Okay, now the nice thing about this is, which is really nice, if you've got a basic series like this, and again, I want to show you where it converges in a minute because it's a nice one. You can find all other kind of series. So, for example, here, suppose I wanted to get a series for e to the minus x. Now, let me go back up here to what e to the x was. Suppose I wanted to get one for e to the minus x. Well, you know what? All I have to do, if this is e to the x, all I have to do here to get e to the minus x is replace every x with a minus x. So I just replace that with a minus x. Everywhere there was an x, I put a minus x in here. That will give me an estimation of e to the minus x. Now, that's very powerful in science because a lot of times you cannot figure out what the integral of something is. So I'll give you the example I gave you a minute ago. In statistics, I wish I had the formula right here in front of me, but I don't. E to the minus x squared is that thing that's part of the normal curve. And finding area under the normal curve is important. You know, what the probability that you're going to be under the normal curve is 1. What's the probability you're going to be in a certain area of the normal curve will be an integral, okay? I can't integrate that. I can't integrate it normally. But if I rewrite it as a power series, I can integrate it term-wise. So all I'm going to do is everywhere there's an x, let me back up a little bit here. everywhere there's an x in my e to the x series, this one right here, I am going to put a minus x squared. So it's going to be 1. And again, I can't see it. But the next one will be plus minus x squared to the first. The next one will be plus minus x squared squared over 2 factorial plus minus x squared cubed over 3 factorial, and so on. So that's what and this is going to be that one. This one will be alternating. That one was alternating too. This will be alternating as well because of that minus in there. So if I want to find an area under a curve that's got that in it, I'll just take the integral using this thing. And the further I go out in that integral, the better the approximation will be. Let me rewrite this. That's a minus x squared. Doesn't look very good. Okay. And then plus dot, dot, dot. Okay. All right. Questions, anybody? Does everybody sort of see what I'm doing here? If I wanted e to the 2x, guess what? I'd go back to the series for e to the x, and everywhere there's an x, I'd put in a 2x. Put a 2x in here. I put a 2x in here and square it. I put a 2x in here and cube it, and so on and so forth. Okay? So that's pretty powerful. Now, let's look at another one that's even better. Or something else to do. If I said, something else you can do. If I said, I want a series representation of x e to the minus x. Now, then what I'm going to do is take the e to the x series, and everywhere, just like I did a minute ago, put that in. I'll put minus 2x in everywhere. And then, if it's got an x in it, if it's being multiplied by x, I'll just shoot an x through this thing. But let me sort of show you what's happening here, and I'll show you some simplification things you might want to look at. That's what I'm going to do to get, and it's going to be an estimation of that function right there. I'm going to write this for right now, guys. I'd like to write this as a power series. So it's going to start from n equals 0 to infinity of minus 2x to the nth, because I'm raising minus 2x to a power every time, over n factorial. And if you start at n equals 0, anything to the 0 is 1, and 0 factorial is 1, so I start at 1. Okay? Now, does everybody see what I did there? I just did the e to the minus 2x. And then I wrote its powers of minus 2x, and it's n factorials down here still. What you can do, you know you're going to shoot x all the way through it. So we can move the x inside here. It's just like multiplying every one of those terms right there by x. Now, having done that, it ends up being the x is on the inside. Well, what you will see if you do that is that now your powers of x are what there, guys? You got an x and an x times the nth, x to the nth. That should be x to the n plus 1. And that's where they got that n plus 1 by an x in here. If I had shot an x squared through here, there would have been x to the n plus 2 there. But that's a series representation of x e to the minus 2x. So you can build all these functions from sort of a basic function that you know. Now, we don't know a lot of basic functions yet, but we're going to get some important ones. Question on that? Part of your homework, guys, is to do some of that. And it's really pretty easy. And they're all built on e to the x because it's really, well, for right now, because that's the only one we've had so far. All right, let's look at this one. Find a power series representation for f of x is the natural log of x plus 1. Now, in no way does that look like a geometric series. I can't. It's even stranger maybe than e to the x, okay? However, we know that the integral of 1 over x plus 1 is that. Now, I didn't just pull that out of my hat. it's because it's in a certain form and I want to use it, and we know that. Everybody agree with me? The integral of x, 1 over x plus 1 is log x plus 1. Put a plus c on it if you want, but we'll just do this for right now. Okay. Now, what I know then, and why this is important, is that does look like a geometric series. And it looks like a geometric series where x is minus x, or where r is minus x. If I just turn this around and write it as 1 minus a minus x. So a is 1, and r is minus x. So I get this series right here. And again, that's for 1 over 1 plus x. Now, what I said I wanted, that's not quite what I wanted. What I wanted was the log of that. Well, that's kind of nice because there's the series representation. We know the integral of that is the log of that. So I'm just going to take this series right here and I'm going to integrate it. Okay? And actually, technically we would say this, the integral from 0 to x of 1 over 1 plus t, but it turns out to be essentially the same thing. I integrate it and then plug in x. But look at what happens if I integrate this. The integral of 1 is x. The integral of minus x is minus x squared over 2. The integral of x squared is x cubed over 3, and minus x to the fourth over 4, and x to the fifth over 5. Then that is the log, the series representation for the log of x plus 1, the natural log of x plus 1. Just because I kind of had something to hang on to here, I was like, oh, well, I do know something about this looks geometric, and the integral of that looks like that. So I'll write that one, take its integral, and I'll have what I need. Okay. Question about that, anybody? So you kind of got I'm picking and choosing ones that work pretty nicely, but I'll let you practice it later. So suppose now I wanted to estimate the log of 1.1. Now I did it on the calculator, and I got 0.09531011798. If I use 3 terms of this thing right here, see, this is 1 plus x. So if I want to estimate 1.1, I would let x be 0.1. So I'm going to plug in 0.1 to the first 3 terms of that. I'll get 0.1 minus 0.1 squared over 2 plus 0.1 cubed over 3. And when I estimate that, I got 0.0953. That was actually good to 4 places. And I put that line over to indicate to you that it's repeating, guys. But that's pretty good. It was a pretty good estimation. If I want a better estimation, I'll go further out in the series. Okay. In science, there are things, I don't know, you probably hadn't heard of these, but they're Fourier series and Laplace transforms that have to do with series. People do a lot of science like this because in science you get some things you can't integrate, okay, and you can find these series representations. Okay, so let's do one more, and then we'll talk about where e to the x converges. This one says find a power series representation for this. Again, it looks enticingly like a geometric series, but it's not because it's got that square on it. And I can't, even if I square it out, it doesn't look like it, and then I can't really split it up. Partial fractions goes nowhere with this. What I do know is that the part that's just this part without the square has a derivative of that, minus 1 over 1 plus x squared. Now I got a connection. So if I took the derivative of this, okay, or if this is the function, and I want to find this, then what I would do is take a look at the series. I'm going to write this one. It's a geometric series again that looks like this. All right. And what I'm going to try to do is, again, what I know, let me write down what I know because I'm going to scroll away from it in a minute. What I know is that if f of x is 1 over x plus 1, and what I'm looking for is f prime of x, which is minus 1 over 1 plus x squared. 1 plus x squared. All right, and you can verify that. The derivative of that is that. Then if I want this one, how could I use this one to get it? Let's scroll up here. All right, so I know this one right here. All right, I'm going to write it out right there. There it is right there. And if I want to know, I know it's the derivative of that one. I'm just going to take the derivative of this, and I'll have it. I will have it. I will need a, and I'll need a. Well, the derivative of that will be the derivative of this. Okay, because that's f of x is 1 over x plus 1. If I take the derivative of 1 is 0. Derivative of minus x is minus 1. Derivative of x squared is 2x minus 3x squared, and so forth. I wasn't asked originally for the minus. The minus just came along with the package when I differentiated it. So if I really wanted this one, which is the one I originally wanted, then I'll just take what I've got right here and multiply the whole thing through by negative. So when I multiply it through by negative, it changes all those signs, and there's a power series representation for that one. Now, only because I could get a link here between a power series, a geometric series that I knew, and the one I wanted was sort of linked by either integration or differentiation, could I do that? All right, one other thing, and we'll call it a day. This is the homework. I've added one that was not on that page, that I did not have on the original assignment sheet. I added 21, guys. So I think 21 is a good one to look at. All right, let's talk about where e to the x converges, because we now have a power series for that. E to the x, always remember it, 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial. That's what that looks like. That's the series representation there. Now, one thing I might want to know is, where does it converge? Well, when I write it, it looks like this. The sum from n equal, whatever, 1 to infinity of x to the, well, I'll start it at 0, of x to the nth over n factorial. That's what it looks like. I want to use the ratio test to show you where this converges. Let me get rid of the rest of this stuff here. Ugh. Just another little practice on the ratio test. By the way, guys, tell me what the domain of e to the x is. Just in general, what's the domain of e to the x? Anybody?
1 to infinity.
No, actually, it's you're thinking about the range going up. It's from, the range is 0 to infinity, but the domain is minus infinity to infinity. E to the x looks like this. Its domain, it extends indefinitely that way and indefinitely this way. It's minus infinity and infinity. All right, I'm going to use the ratio test to find out what the convergence on this thing, where this thing converges. The limit as n goes to infinity. Limit as n goes to infinity. And I'm going to put in x to the n plus 1 over n factorial. And x to the n, over n plus 1 factorial. I gotta put my plus 1 in there. N plus 1 factorial. And x to the n over n factorial. When I invert and multiply, I get the limit as n goes to infinity. X to the n over x to the n will just leave me with an x. And if you look at the n factorial over n plus 1 factorial, when you invert, you'll get n plus 1 in the denominator. You get 1 more down here than you had up there. if I look at that, it's, if I pull out the absolute value of x and look at the limit, it's times here. Look at the limit there. It's absolute value of x times the limit now as n goes to infinity of 1 over n plus 1. What is that limit right there, guys? What's that limit right there? What? Damn, I got rich. Excuse me. The limit as n goes to infinity of that thing right there. What is it?
0.
It's 0. So it doesn't really matter what x is at all. You'll get 0. 0 is always less than 1, which says what about where that converges, guys? There were only 3 possibilities. It converged on an interval, it only converged at one tiny little point, or it could converge where? Everywhere. That's one that converges everywhere. Because you got this absolute value of x less than 0. I don't care what the x is. You multiply this times 0, you get 0. It's less than 1. This converges everywhere. So we'll say it converges from minus infinity to infinity. So you got a power series that now you can find e to the anything. You can find e to the 5th if you want. E to the 100th using this thing right here. Because it doesn't matter what x is, it converges to this thing. This series converges to e to the x everywhere. Okay, so do the power series representations, because tomorrow I'm going to give you 2 or 3 of those to do for homework to hand in Monday. These will not take you long, I do not think, because you're just going to work with e to the x and just plugging things in. So maybe you can catch up tonight. Maybe I can catch up grading papers tonight. Who knows? Questions, anybody?
I have a question.
Yes, ma'am.
It's about the last problem you went over on the homework from yesterday, the partial fractions one.
Okay, let's see if I can find it. Let's see if I can find it here. It was back before this, right there.
Yeah.
That the one?
Yeah, my only question is,
Mm-hmm.
why is this it? Oh, this is.
Is that it?
I don't know. But anyways, no, this isn't it. No, I don't think so. I don't know. Whatever.
What was your question, though? Tell me what your question.
The question was, I subtracted the 2 and you had a plus sign in between. I don't know why.
Did I find out that?
I don't know.
Oh, wait a minute. Did I find out that A was? I'd have to do the partial fractions again. Good question. Let's just do it real quickly. Anybody that needs to go can go. Let's just do it real quickly and see what it should be, because I definitely could have messed up there. Okay, let's do the partial fractions. Good review. So if I look at 3x minus 1 over this factor form, x minus 1, x plus 1, it's going to be a over x minus 1. Let's make it, yeah, plus b over x plus 1. Okay, if I multiply through, I'll get 3x minus 1 equal a times x plus 1 plus b times x minus 1. If I match the coefficients, I get a plus b has to be 3. You can use the Heaviside method if you want to. I just did ax and bx. And then a plus a minus b has to be minus 1. If I add, I get 2a equal 2, which means a is 1. So the 1, this is a 1. And if a is 1, b is 2. It should be a plus. It should be a plus. Okay. Is that your question?
No.
Maybe. No. Well, anyway, it should be a plus.
Because this is the example problem you gave us. For the homework, it was 3x over x squared plus x minus 2.
Okay. Look at it. Let's go down here and look at it. Okay, give it to me again. F of x is what?
3x
Mm-hmm.
divided by x squared plus x minus 2.
Okay, so if I factor that, I get an x, a 1 and a 2, a plus and a minus. That'll be a over x minus 1 plus b over x plus 2. And if I multiply through, that says 3x is a times x plus 2 plus b times x minus 1. So the x coefficients, that's a b there, sorry. The x coefficients are a plus b is 3. And 2a minus b is 0. 2a minus b is 0 because there's the constant over here on this side, 0. Okay, the b's drop out. I get 3a equal 3, which means a is 1. There's a 1 up there. If a is 1, b's got to be 2. So that's a 2. So what's your question? Did I do it right here?
Yeah, I have that exact same thing. You're right. But my question is,
Okay.
at the very end, you know how we get the intervals and stuff? Like
Yep.
I got one was -1 to 1, and the
Mhm.
other one was -2 to 2.
Uh-huh.
And then I don't know. I saw at the end of yours, it was like basically you said that the first series plus the other series, and I got minus in between that. I don't know what I'm saying.
All right. Let's look at what you're saying here. Let's just see what happens. This is 1 over x minus 1. So if I wrote that as a geometric series, it'd be -1 over 1 minus x. I can make that easily, right? Okay. So that means that a is -1 and r is x. That means this is going to converge for absolute value of x less than 1, which means it's going to be between 1 and -1, and the series is going to look like the sum from n equals 0 to infinity of -1 times x to the nth. That's that one. 2 over x plus 2 looks like that. But now I need to divide by everything by 2. So that's 1 plus x over 2. I need to rewrite that so it has a minus in there, right, Tiara? You on board so far?
Yes.
Okay. So that's 1 over 1 minus a minus x over 2. So in this one, a is 1, r is minus x over 2. But that'll converge where minus x over 2 is less than 1. The absolute value of a minus is going to be positive here. So that's going to be absolute value of x. If I multiply everything through by 2 and take into account that the absolute value of -1 is 1, so that's like -1 times x, so I can get rid of that. Over 2 is less than 1. If I multiply through by 2, I get x, absolute value of x less than 2, which means x is in between 2 and -2. So that one converges on a larger interval than that one converged. And the series in that one would look like the sum from n equals 0 to infinity. My a was 1, my r was minus x over 2. So I raise that to the nth power. There's that. So what's your question?
So that's it.
Well, if I say to you, where does the original converge? You got to pick the smallest interval that both of them converge on.
Okay.
Okay, so what is that smallest interval?
-1 to 1.
Yes. So here's the way I would envision that, Tiara. This first one converged from -1 to 1. This second one converged from -2 to 2. If you want to see where the two added together converge, you just have to pick the overlap. And the overlap is that, right?
Yeah.
That makes sense? Okay. So that's what happens there. So you got to pick the least interval there, or whatever the overlap is. because these are no good out here because that one does not converge out there. So when you put them together, you'll see that. Okay. So I'll put that key up and you can look at the rest of them and make sure you got them right. It looks like you pretty much understand how to do this.
Yeah, that was the only one where it took me a second to get, because I had to go back to how to do partial fractions.
Yeah, I know. But you know what? Partial fractions is a weird thing. You think, first see it in calculus and you think, wow, when am I ever going to use that? And it pops up everywhere. Pops up everywhere. Okay. Anything else?
No, that was my only question.
Okay.
Wait, one more.
One more. Okay.
Wait, the quiz on the ratio test / all that policy, all that other stuff.
Mm-hmm.
What does that do?
What'd you say?
That's what is the one Moodle. What does that do? The one that we didn't turn in. If you don't know, that means it's not due, and that's okay. I
want it by class tomorrow, okay? I think I said today, but just get it to me by class tomorrow. I'm not even going to be able to work on it tonight, okay? I don't know. I think Alexis sent one. I didn't even see who sent me one. And I should have put the due date on the Moodle, on the assignment sheet, but I didn't. Just get it to me by tomorrow, okay? Since you've already done all this, the homework's not going to take you very long. I think you can sit down and do that thing in 20 minutes.
Maybe.
I think you can. So send it to me as soon as you get it done, but not later than class tomorrow, okay?
Okay.
Okay. All right.
Gotta watch some TV first. Gotta get my mind right.
What's on TV?
I don't know yet, Harold. I'll figure it out. But I just need a mental break for like 2 hours.
I know. I need a mental break too, but every time I turn on my TV, somehow it merges into MSNBC and I just get depressed. I should watch Andy Griffith or something. I don't know. I've got to watch something. Yeah. You got to take a break from the news.
Exactly.
We're living the news, so we don't need any more news, okay?
Exactly. We're in quarantine.
It's weird. It's totally weird. When you're an old lady, you're going to be talking to your grandchildren about, I remember the quarantine, like people talked about the Depression for me. I was like, I grew up during the Depression. And I'm like, so what? Anyway.
Well, they're going to say, so what, tell quarantine. Oh, man.
Yeah. Anyway, there was this funny thing online on Facebook that somebody sent me, and it was a kindergarten teacher in 2025, and she was reading out the names of her little kids, of her 5-year-olds, okay? And so 5 years from now. And she started looking at these names. She said, okay, your name is Quarantina. We'll just call you Tina. The other was, and then they would say, your name's COVID Alex or something. People were naming people things about what was going on the year that those 4 kids that got those names were born. So it was funny. It was on Facebook. So anyway,
they're never going to be able to live those names down.
That's true. You have to be careful with names. So
very careful.
Yeah. All right. Anything else?
Nope. I'm fine.
Okay. Have a good day. Go watch some TV.
I will. You too.
All right. Bye.